This video walks through how to use the single case design hierarchical linear modeling SCDHLM web app for calculating design comparable effect size estimates for data from single case designs that involve time trends in the baseline and/or treatment phases. The point of the design comparable effect size for SCDs is to provide an effect size index that is on a scale comparable to the scale of effect sizes used for between group experimental designs. In other words, it answers the question, how big an effect size would we expect to see if we could have somehow conducted a between group experiment with these participants using the same intervention and same outcomes as in the study we actually conducted. As you'll see in this demo video, calculating a design comparable effect size estimate for a single case design involves a bit more work than just plugging some numbers into a formula. This is because the effect size estimate is based on a statistical model, a hierarchical linear model to be specific, as well as some assumptions about the hypothetical between group design that we're trying to emulate. To get an effect size estimate, we'll first need to load in the data, visually inspect the results, and arrive at a reasonable statistical model for the data. Once we've identified a reasonable model, we'll then need to make some assumptions about the hypothetical between group design we're trying to emulate. Based on all that, the app will give us an effect size estimate along with a standard error, confidence interval, and other information. To demonstrate this process, I'm using data from a 2021 study by Derek Rogers and colleagues. This study used a multiple baseline across participants' design to investigate the effects of explicit instruction with time practice on the fluent sentence text writing and sentence construction of 4 post-secondary students with intellectual and developmental disabilities. Once I've accessed the SCDHLM web app, I start by clicking onto the Load section where I can upload my data. Here, you have the option of selecting an example dataset, which is helpful if you'd like to practice using the calculator. You're also able to upload data from a .csv, .txt, or an Excel file. I'm uploading an Excel file, so I will select Upload Data from a .xlsx file, click Browse, and then locate the file with my data. The first box asks if the file includes a header. Mine does, so I keep this box checked. I'm also given the option to select the sheet of my file where the relevant dataset is located. My file has several sheets, but I know that the dataset I need is in the sheet labeled Rogers 2021, so I can select that. I then need to specify the study design. Mine is a multiple baseline across participants design, so I will select multiple baseline / multiple probe across participants. Now I need to map my variables from the file to the variables used in building the model. The app will make guesses about which columns correspond to which variables, but they're not particularly smart guesses. It helps if you can arrange your data so that the columns are in the same order as appears in the app. Case, phase, session, outcome. This data does not have the variables in that order, so I need to modify things a bit. My case identifier is case. My phase identifier is condition, my session number is session, and my outcome variable is outcome. I also need to use the drop-down menu to specify which unique entry of the phase identifier column indicates baseline and which indicates treatment. In my case, I make sure that my baseline identifier is baseline and my treatment identifier is treatment. If your design has other phase labels in it, like maintenance for a maintenance phase, the observations from those phases will be excluded before fitting the model. The last optional input is to select a filtering variable. This is useful if you've got a big data set that includes some rows you don't actually want to use, such as data from cases that received a different treatment. I'll leave this blank. By the way, this dataset is actually included as one of the example datasets in the app. If you would like to follow along with the remainder of this demo, you can select Use an Example and then choose the Rogers data from the drop-down menu. Once I've got my data loaded in or selected, I can then click on Inspect to take a look at the graphs of my data. It's a good idea to compare the graph displayed here to the graph data from the original study to make sure that the dataset was uploaded accurately and that you've selected the design and variable names appropriately. Here, I can take a look at the Data tab to double check that. The graph displayed on the Inspect tab is also useful for purposes of assessing what model to use for estimating the design comparable ES. The model choice involves deciding a couple of things, including whether to include time trends in the baseline phase, whether to include changes in time trends during the intervention phase, and whether the time trends and other aspects of the model are similar across participants or vary from participant to participant. To determine what model to apply to the data from this study, I consider both theoretical expectations and visual inspection of the data. In terms of theory, I consider what I know about the characteristics of the participants, their context, and the outcomes of interest. Based on what I know, would I expect there to be systematic time trends in the outcome? Would I expect that the participants are relatively similar and should have very similar time trends, or would I expect any time trends to be different for different participants? Considering what I know about the intervention, would I expect there to be shifts in the time trend as a result of treatment? Or alternately, would I expect the treatment to pretty much immediately shift the level of the outcome? In addition to theoretical considerations, it's also important to consider the pattern of outcomes in the real data using careful visual inspection. We may look at the data and recognize no trend, linear trends, or some form of nonlinear trends in the baseline phase. We should also consider whether the baseline trajectory, meaning the level and slope, differs across cases within the study, or if either the level or the slope appears to be constant across all cases. Similarly, we will also want to consider whether the trajectory once treatment begins, meaning the change in level and change in slope at the start of the intervention phase, vary or are constant across cases. In viewing the graphs, I can see a potential downward trend in the baseline phase for some students, while other students seem to have stable baselines without noticeable time trends. This indicates that I should select a model that allows for baseline time trends that could differ from student to student. I can also see a slight upward trend in the treatment phase, and the slope of this trend looks like it might vary across students. This indicates that I should select a model that allows for varying trends in the treatment phase as well. Now that I've visually inspected my data and have a good sense of the assumptions I want to make about time trends, I move on to the Model tab to specify the model for the design comparable ES. The estimation method dropdown allows me to select between restricted maximum likelihood or moment estimation. I'll keep the default of restricted maximum likelihood, which is the recommended method. I then bring my focus to the types of time trends in the baseline phase. I'm assuming there is a slight downward trend in my baseline phase, so I can select linear trend. I opt to include level as a fixed effect and a random effect so that the estimation of the average baseline level varies from case to case. You'll pretty much always want to include a random effect for baseline level to allow each participant in the study to have a unique initial level of performance. I also want to include my linear trend as a fixed effect and a random effect so that the baseline time trend can vary across participants. I now look at time trends in the intervention phase. Here, I select change in linear trend because based on my visual analysis, I noted that there is a slight upward trend in the treatment phase, which differs from the time trend in my baseline phase. I make sure to select change in level and change in linear trend as fixed effects because I'm assuming that the treatment changes the level of the outcome as well as the linear trends. I will also include change in level and change in linear trend as random effects to allow the treatment effect and trend to vary from case to case. Including these random effects means that we are assuming that each of our cases may have different treatment effects and growth trajectories as a result of the intervention. The last two drop-down menus under Session Level Error Structure Assumptions let me select a correlation structure and variance of session level errors. These are more advanced options, so most users will probably just use the default values unless they have a good rationale for doing otherwise. The correlation structure allows me to choose which model will be used to describe the observation level errors. The choices are an autoregressive model, AR1, which uses regression with previous time points to predict values at the following time point, a moving average model, MA1, which predicts each observation as the mean of past observations, or an independent model, which assumes that the deviations from the mean, in other words, the observation level errors, are all independent. When deciding on a choice for the variance of session level errors, I can choose to assume homogeneous or heterogeneous variances for different phases. If assuming heterogeneous variances, I choose variance differs by phase. Here, I'm keeping the defaults of AR1 and constant variance because I don't have a strong reason to use other assumptions. Now, at the bottom of my screen, I see the graph of the data with predicted trend lines based on the specified model. Inspecting the graph lets me see if the trend lines fit the data reasonably well and gives me the chance to reconsider my model selection if necessary. Clicking on the Model Estimates tab gives me a display of the model parameter estimates based on the model specification I've selected. Underneath the hood, the app is estimating a hierarchical linear model for the observations nested within participants. If you're familiar with hierarchical linear models, you might find it interesting to look at the numerical results for the estimated model. If you're not familiar with HLM, you can focus on interpreting the graphical representation of the fitted model. Here, I'm also able to select a value at which to center the session variable. This selection is only relevant if looking at raw model estimates. If you're only worried about your effect size estimate, this selection is irrelevant. Now that I've settled on a model specification, I can proceed to the effect size sections to finalize the calculations and obtain an effect size estimate for the study. I can use the sliders at the top to alter the hypothetical experimental parameters for initial treatment time and follow-up time. While the app populates times automatically for each, I can manipulate them manually to obtain the treatment effect at the desired point in time. The selection of these times matter when you've selected a model where the baseline time trends vary across participants, or when time trends differ between baseline and intervention phases, as in the model that I have specified. The default choice for initial treatment time is the last measurement occasion of the shortest baseline phase across cases. This time point tends to be somewhat arbitrary, and we recommend using the default choice unless you have explicit justification for selecting a different time point. So here I will leave the initial treatment time as the default. The default for the follow-up time corresponds to the shortest treatment duration across cases. The default was chosen to limit the extent of extrapolation. When selecting a follow-up time, you should consider previous research that uses similar interventions for the same population, either from between group designs or single case designs. However, if no convention or guideline is available, we recommend keeping the default choice. In my case, the default follow-up time is not meaningful. Based on the research context of our study, we want to estimate the treatment effect 12 observations into the treatment phase. So we can set our follow-up time to 21. I can now see that my BCSMD estimate is 0.77 with a standard error of approximately 0.73 and a 95% CI of negative 1.3 to 2.8. This tells me that, based on this model, the intervention shifts the outcome by about 0.77 standard deviations, but this is quite a noisy estimate because the confidence interval is very wide. The ES can also be interpreted as an estimate of the standardized mean difference that would be obtained if we could have conducted a between-group experiment involving the same set of participants, same intervention, and same dependent variable measures, and where the intervention lasted 12 sessions. One important thing to recognize about the BCSMD estimate is that it can be bigger or smaller depending on your selected follow-up time for the hypothetical between-group experiment. For example, Suppose I used a follow-up time of 33, so that the effect size is describing the effect of 24 intervention sessions. Using this follow-up time leads to a BCSMD estimate of about 0.7 with a standard error of 1.3 and a 95% CI of approximately negative 4.16 to 5.57. So you can see that in some cases, the choice of follow-up time can make a meaningful difference for the effect size estimate. Because of this, it is important to try and select times that are plausible and justifiable. I now move my follow-up time back to 21 to continue interpreting the remaining numbers in this table, which provide auxiliary information about the model that the ES estimate is based on. The table reports the degrees of freedom, here 3.9, which are used in making a small sample correction to the effect size estimate. The larger the estimated degrees of freedom, the less consequential the small sample correction made, and the more precisely estimated is the scale of the effect size. Then I have the reported autocorrelation, here about negative 0.42, which is the estimate of the correlation between the level 1 errors of the model for the same case, different by one time point, based on a first-order autoregressive model. We then have session-level errors variance parameter, which we'll come back to in a moment. Lastly, I have the reported intraclass correlation, here about 0.4, which describes the between-case variance of the outcome relative to the total variance in the outcome. Larger values indicate that more of the variation in the outcome is between participants. The session-level errors variance parameter becomes relevant when allowing variance to differ by phase in the development of our model. For example, if I go back to click on the Model tab and select if variance differs by phase, the Estimate tab will now show the number 1.0452, which is the ratio of the standard deviation during the treatment phase to the standard deviation during the baseline phase. The remaining information describes the model specification and assumptions used in the ES calculations. It is included to allow for reproducibility of the calculations. Clicking on Download underneath the table downloads a .csv file onto my computer that includes all of the information in the table. Finally, clicking on the Syntax for R tab provides auto-generated R code that I can then copy and paste into R for replicating the calculations. To demonstrate, I can click Copy here and then paste this into an R script. Saving this R script can be helpful if I need to rerun the calculations. Running the code provides me with the outputs ES_RML and FIT_RML, which provide the same results as we saw in the SCDHLM app. In this video, I've demonstrated how to use the SCDHLM app to estimate a design comparable effect size for a multiple baseline across participants based on a model that includes time trends in the baseline and treatment phases. Of course, this is only one model specification. In using the app with your own data, it is important to select a model that is informed by your theoretical expectations and provides a reasonable fit and approximation to the patterns you observe in your data. Doing so might mean you make some different modeling choices than what I've demonstrated here. To learn more about the methods and approaches implemented in SCDHLM, check out the tutorial paper and other resources listed on the front page of the app. Happy modeling!